Hi everyone. Today let's talk about Chapter 9, Trees. Session 9.1, Trees and Definitions. So a tree T is a simple graph satisfying the following. If V and W are vertices, there is a unique path from V to W. Okay, so what does that mean? So if we have a V and W there is a unique path joining them. Okay, which means we don't allow to have this case. Okay, so we don't allow to have this case. So no parallel edges. Actually, no cycles. Okay. So no cycles because we don't want to have like different way to pass through it. Okay, so no cycles, and also we want it to be connected. So we don't want to, like this case, this vertex is isolated, so we cannot reach this vertex, right? So it has to be connected. Okay. So a tree, by looking at this definition, we know it won't have cycles and it is connected. Next, a rooted tree is a tree with a particular vertex designated as the root. So a rooted tree is really like a tree upside down, right? You have the roots on top and then we have the branches down there. Okay, so we have a vertex designated as the root. Okay, in graph theory, the roots are usually at the top of a tree, although the top and the bottom are somewhat arbitrary. Vertices in a tree has levels. The level of a vertex is how many edges you must travel to get from the root to the vertex. So that is the length of the path. Okay. So for example, this picture, the roots we have level 0, and then these vertices we have level 1, and these guys we have level 2. Okay, it's the length of the path that start from the root. Okay, next, the height of a tree is the greatest level of the vertices in the tree. Okay, so like this picture, the greatest level is 2, so the height is 2. So far, so good? Generally, any vertex of a tree can be designated as the root, but once designated, then the level of each vertex can be determined as well as the height of the tree. So yeah, a rooted tree we must designate the roots, and then all the level and the heights are fixed. Usually there is a reason a specific vertex is the root according to what the tree represents. Okay, let's look at some examples. So example E, we want to designate E. Designated the E as the roots in the tree T and draw a rooted tree T prime. What are the vertices with level 2? What is the height of T prime? So here E is the root. And so we have E on here. And then you can see what are the vertices adjacent to E. That is B, D, F, G, right? So for the vertex adjacent to E, that's gonna be the first level. So we have B, let me put it smaller. So B, D, F, G. Okay, and then let's look at B. B, what are the vertices that are adjacent to B? Well, that's A and C, right? Okay, how about D? Oh, by itself. F by itself. G, we have I and H. So let's say H and I. The order doesn't matter. And then for I, we see there is a J down there. Okay, so this is the rooted tree T prime. So far, so good. and the root, so E is the root, and that is level 0. And then B, D, F, G, they are level 1. And then A, C, H, I, they're level 2. And the J is level 3. Okay? And then here, what is the height? So the height is the highest level, which is 3. Okay? So the height in this case equals to 3. Okay, so what are the vertices with level 2? So we can say level 2, we have A, C, H, I. So far, so good, everybody? Alright, and let's go to next example. Hierarchical relationships. A is above B if A dominates B, or B is subordinate to A in some way. So, for example, we have administrative organizational chart of a university. The other examples, we can consider positions at a company. Okay, so we have the president, that's the root. And then next we have the vice president for academic affairs, and also the vice president for administrative affairs. So this is just one example, okay? And then under vice president of academic affairs, we have the deans of arts and science. We have the deans of business. At Indiana Tech, we also have deans of College of Engineering, right? So this graph is just an example. And then under the deans of arts and science, we can have chair of mathematics, chair of computer science, etc. And under deans of business, we have chair of accounting. Okay, and then we also have some faculties under it. Okay, so I think I'm right here. So far, so good, everybody. Okay. And here we also have vice president of administrative affairs. Then we have directors of academic planning, director of purchasing. So this is just an example. So you can see through the rooted G, it really shows us the hierarchical relationships. Okay, who is above who? Okay, next. Next example, our computer file systems. All of us have computers, right? Computers organize folders and files using a tree structure. So for example, here, look at those files. You can see here, those files is under the folder basement water. Are you able to see it? And then you can see my ebooks and archive. And then next, they're under the my pictures. And then my pictures, my photo shows. Is this my photo shows? Okay. And my data source, my ebooks. Those together are under the FAS. Okay. And then FAS is under my documents. And then then documents is under desktop. So you can see here, start with desktop, and then we have my documents, my computer, my network place, and then under my documents we have FAS. So FAS, we have my data source, my ebooks, my photo shows, and then under my pictures, let's see, I think my data source is under the FAS, right? Okay, or it's not. Okay, sorry, the picture is so small I cannot really see it. Then my picture, we have archive, basement water, and my ebooks, and then we have those files. So far so good, everybody. So you can pick any folder of your computer, and then you can also draw a trees to represent the how your folders and files are organized in your computer. Okay. Next, hierarchical definition trees. A hierarchical definition tree shows logical relations among records within a database. Examples. The following is a model of setting up a database to maintain records about books housed in several libraries. So we have books, and then for a book we have author, locations, and publisher. And for the location is either available or not available. Okay, so this is the example. You can see so many trees that are so useful. Next, Huffman code. So the most common way to represent characters internally in computer is by using a fixed length bit strings. For example, ASCII, American Standard Code for Information Interchange, represents each character by a string of 7 bits. So this is a fixed length. Okay, so fixed length bits. For example, this is some table. A is represented by 1000001. B is represented by 1000010. Okay, so all the letters is we have a code for it is 7 bits. Okay. Because all of them have 7 bits, so it's quite long. So Huffman code, which represent characters by variable length bit strings, provides alternative to the American Standard Code and other fixed length codes. The idea is to use short bit strings to represent the most frequently used characters, and to use the longer bit strings to represent the less frequently used characters. So this is not a fixed length, but sometimes it's easier, okay, because some most common used character is we have shorter bit strings. Okay. Next, to decode a bit string, we begin at the root and we move down the tree until a character is encountered. So the bits 0 or 1 tell us whether to move to the left or the right. Okay, so let's look at this example. What does 0010111 spell? So we start from the roots. So 0. Okay, and then 0. See, now we have reached the O. So 00 gives us the O. Okay, and then once we encounter a letter, a character, then we go back to the roots. So 1, see, 1. So this guy, the 1, gives us the A. Because we encounter the character, so we go back to the roots. So 0. And then 1, and then 1, 1. See? So this 4 bits strings give us the T. So this total gives us OAT. Isn't it interesting? Alright. Let's do some more examples. If I just make up a number randomly. Okay, I just make it up randomly. Let's see whether it works. So 1 give us A, and then 0, 0. Oh, give us O, and then 1 give us A, and then O, 1, 1, 1 give us T. Oh, and then there's 0. Okay. So this 0 is not enough. Let's put 0, 1, 0. Then 0, 1, 0 give us R. So far so good, everybody? Yes. Okay, so with the Huffman trees, you can sometimes you can create some secret code with your friends. Okay. Then because only you and your friends know this tree, so you guys can decode. Okay, next, encode the word SAR. So S is right here. So S is 0, 1, 1, 0. So S is 0, 1, 1, 0. A is 1. R is here. 0, 1, 0. So far, so good, everybody? Alright. How about, let's see. Let's do more examples. How about, let me just make it up something. So, TASOR. Okay, if we want to encode this word, then let's see. Feel free to pause the video and try to work on this, and then you can continue to play the video and check your answers. Okay, so let's see. T is 0, 1, 1, 1. 0, 1, 1, 1. That's the T. A is 1. S is 0, 1, 1, 0. And then O is 0, 0. Oh, sorry. My O really looks like the 0. And R is 0, 1, 0. So far, so good, everybody? Alright. And that's it for sessions 9.1. Okay, so in this session, we talk about trees, and we went over some examples about the trees. Okay, so if you have any questions, feel free to ask me either in class or office hours or email me. Have a nice day. Bye.